Thank you, Kelsey. And welcome to Berlin, everyone. Kubernetes, this is a great time to be involved in the Kubernetes project. This project is attempting to redefine how the world runs applications on distributed systems. And we believe that this is only possible through an open and transparent and diverse community of users and contributors. You all know that containers are portable, and that is a huge part of their value to users. But you also need a portable management stack to go along with that. So you want a stack that can run on-premise, in hybrid, and in multi-cloud environments, as well as locally on your laptop and maybe on Raspberry Pis for the hobbyists. We believe that in order to achieve this level of applicability across environments, it takes a large community that works across the world, just like our users are across the world. And the openness and transparency lets us stay honest, and it gives the community feedback about whether we're building the right product and heading in the right direction. So I'm going to give you some examples of this. Kubernetes 1.6 just released sometime in the middle of the night yesterday. We're very excited. The theme for this release is multi-team, multi-workload at scale. And it is a result of 5,000 commits across 275 authors from everywhere around the world. Release management for 1.6 was led by Dan Giuseppe of CoreOS, and this is the first time that a non-Googler has led the management of the release. So Kubernetes now supports 5,000 node clusters. That's within the same stringent SLO that we had before. But did you know that this feature was done here in Europe? The Google team in Warsaw, all of whom are here in the audience today, contributed and led to the testing of 5,000 node clusters. And if you like my blue hoodie, this is a special Warsaw edition Kubernetes hoodie, and you can catch them afterwards if you want to try and get one. Perhaps the biggest, most important feature in this release is role-based access control. And that work was led by a team from Red Hat involving many other companies in the community. And I'm going to do a demo of that. Controlled scheduling allows you to control where you schedule different workloads in a large cluster. This is very important for multi-workload clusters, which ultimately helps you improve the efficiency. And this work was also a collaboration across many companies: Google, Red Hat, IBM, a team in China with Huawei, and many others. The last one that I'm going to talk about is dynamic storage provisioning, which is essentially storage automation in the service of stateful applications. Again, allowing you to run multiple workloads, not just stateless, but stateful in the same cluster. So new features are cool, and product managers and engineers like new features. But how many of you care about stability? Yeah, about 100%, right? So the Kubernetes community as a whole decided that in this release and in many future releases, we are going to focus on stability. That is a core value proposition for our users. And so over 20 features moved from alpha to beta to stable in this release. 5,000 nodes. What does that mean? It means 150,000 pods in a cluster. And really what we've tested is that this still works within the stringent SLO of less than 1 second pod, API latency, 99th percentile, and less than 5 seconds pod startup time, also 99th percentile. But the real hero behind this work is etcd v3 specifically, which was developed by CoreOS in support of this scaling. The data model has been updated. The communication framework has been updated. So data communication, instead of over JSON, is now using the gRPC protocol, which allows much greater performance. So now let's go to whether bigger is better. So now you have a 5,000 node cluster. We ask users, do you want to go further? What do you plan to do with a 5,000 node cluster? Is that really what you're looking for? And what I hear from users is they actually want global scale. They want to serve their users where they are with low latency. And so often it's multiple large clusters in different geographies around the world. That's what this map is trying to show. And we asked users, why is multi-cloud important to you? And it wasn't just about scale. A lot of it had to do with reliability, availability, and ultimately reducing IT infrastructure costs. That's why this release and our roadmap going forward is very focused on efficiency. Making sure that you can run multiple teams without interference within one cluster, and multiple different types of workloads within one cluster in an efficient manner. So the first feature that works on this is RBAC. Without role-based access controls, you have a cluster, whether it's a 3-node cluster or a 5,000 node cluster, that's essentially vanilla. Every pod has roughly the same level of authorization as every other pod. So whether you have a blue team or a green team or different types of workloads, there's not good differentiation between them in terms of the permissions and what they can do. Also, without granular control over scheduling, it limits the flexibility to optimize utilization. That brings me to RBAC. RBAC marks a huge shift in Kubernetes. Tim Hawkin, one of the Uber TLs of this project, draws the analogy to, it's like going from DOS, where it's a single flat user, and everyone can see everyone else's files, to Unix, where it's user-specific permissions. And this is now what it looks like with RBAC. You can separate the workloads of different teams into different namespaces and give them granular permissions on what they can achieve. So let's do a demo to show this. If we could switch over to my laptop, please. All right, we're going to try and do a live demo here. I have a cluster that is running 1.6, our latest release, in Google's cloud and container engine. It's a 3-node cluster. And in order to do a demo of role-based access control, I need multiple roles. So I'm going to star in this movie as 3 different people. I will be, in this window, a cluster admin that has control over everything. It's like a super user in the cluster. And then I'm going to create 2 different accounts. One account for a blue team developer and one account for a green team developer. And I'm going to play those roles in these other tabs. Okay. So here what I've done is I've told the gcloud IAM service, please create an account for the blue team developer and store those keys in a local file. I'm going to do the same thing for the green team developer, and the IAM service is going to create that service account and store their credentials in a local file. And then I'm going to go to the blue team's console here. And configure kubectl in this window to get those credentials. And the same thing for the green team. This is all essentially set up so that you can see three different roles in this cluster. Okay. Now I'm going to create a namespace for the blue team. Kubectl create namespace blue. Let's go over to the blue team and see if the blue team can do anything in this namespace. They shouldn't be able to because I haven't given them permissions. So kubectl get pods namespace blue, and we get an error. And this is as it should be. So I'll show you how I, as the cluster super admin, can set up these permissions. And this gets to the heart of role-based access control. So the core here is a set of cluster roles that are predefined and can be updated to add custom roles. These are some of the user roles. There's also system roles. So some of the user roles, as you see, there's admin, there's edit, there's view. We're probably going to want the admin role for the blue team because we want the blue team developer to be able to create and delete pods and services. So let's take a look at what the admin role default permissions are. This is a condensed version of what those permissions are, just looking at a few of them. So the cluster role admin has access to several resources and sub-resources, and it has the ability to execute these verbs. It can create, it can list, it can set up watches on all of these resources. Okay, so that's great. Now, how do we give the blue developer this role? We need to create a role binding. This is the YAML for the role binding. And what you see here, it's saying that I want to give the role admin to the user blue team developer, which happens to be a service account, in the namespace blue. So let's create this binding. It's been created. Now, if we go to the blue developers console, and we again try and get pods in the namespace blue, we see that we don't get an error. So that is now successful. He has access to the blue namespace. What can he do in the blue namespace? He can actually execute. So now he's created an Nginx deployment, and this is what you would expect. He has admin access to the blue namespace. And now if we get pods, of course, Nginx has created some pods and get services and so forth. So that's the first thing I wanted to show. Let's also do this for the green namespace so we can show the difference and that the green user doesn't have access to the blue namespace and so forth. So we're going to create the green namespace, same thing, and create a role binding. Now we're giving admin cluster access to the green team for just the green namespace part of the cluster. All right, so we'll go ahead and create that. And let's go back to the blue admin and make sure that he doesn't have access to this new namespace that we just created. So get pods namespace green for the blue developer gives us an error. He has everything he can do in the blue namespace, but not in the green namespace. Can't get services, etc. Let's go to the green user for the first time and see if our RBAC worked. And it did. When we do get pods namespace green, there's no resources found. We don't get an error. We haven't created any resources. Let's make sure that this is actually admin access and that as a green user, I can create an Nginx deployment. And looks like that succeeded. And I run forward a little bit. I want to make sure that while he can do anything he wants in the green namespace, he can't actually access the blue namespace. And so get pods blue namespace indeed returns an error. So now you see the isolation between the two teams in the same cluster based on two different namespaces. That's nice. There's a lot more you can do, and I'll show you one last thing. If I want to give the green team view-only access to the blue namespace, so that, let's say that the green team is doing some monitoring for the whole cluster, and I want them to see the pods and services in the blue namespace, but not be able to modify them, I can do that too. As the super admin for the cluster, I have visibility and access to all the namespaces, so you can see that I have access to the blue Nginx deployment, I can see the green Nginx deployment, and there's a number of system deployments that are there. I'm going to create the blue-green binding. And what that says is let's give view access. So the view was one of the roles I think you saw earlier, to the green team developer in the blue namespace. So view means they shouldn't be able to create anything. So we've established that role binding. And let's go back to the green developer and see that now, if he has access to the blue namespace, and yes, indeed, there's read level access, so the green developer can read and see the Nginx deployment in the blue namespace. But we want to also check whether they can delete this, for example, or take, and so kubectl namespace blue delete deployments does not work for the green developer, and that's as it should be. So this just, that ends my demo. This just illustrates that there's a lot of granularity because we've got namespace level per resource by role permissions that you can set for different types of users. And that gives you a lot of flexibility and granularity in terms of defining and giving structure to your teams and in your cluster. So the next set of features, controlled scheduling, is more about scheduling multiple different types of workloads and optimizing efficiency across those. There's actually three or four different features within this that are moving to beta in the 1.6 release. Node Affinity allows you to define on a per pod basis a preference or a requirement of the type of node on which that pod should schedule. So you can say, I want to schedule this pod only on nodes in this zone, or nodes that have SSDs. Or you can actually define custom labels, and you can label nodes and then decide, and then set which pods should schedule on those nodes. Pod Affinity and Anti Affinity lets you schedule pods relative to other pods that may be there. This is very useful if you want to, for example, optimize interpod communication, such as for east-west or north-south communication. That's pod affinity. Pod anti-affinity is if you want to, for example, separate pods from each other. You want maximum spreading in the cluster, or you want to avoid antagonistic services from co-scheduling on the same node. I'll give you an example of that. Taints and tolerations are on a node basis. You can put a taint on a node that says, this node is dedicated for this team, or this node has a GPU, and so only workloads that tolerate that taint that require a GPU should schedule there. Lastly, custom schedulers give you the ultimate flexibility in scheduling. You can bring your own scheduler that can work alongside or in place of the default scheduler. So I'll give you an example of how to use pod anti-affinity. And what we're doing here is we've got a stateful pod, which is blue state, and it's part of a quorum-based stateful application. So we want to make sure that there's always, the pod is scheduled on a different node. Each pod is scheduled on a different node, and not together. And also that at least 2 of these pods are up at all times. So there's 2 features here that we're using. Pod anti-affinity, where we're saying that do not schedule. The effect is do not schedule. The key is host name, so do not schedule on a node where the value of the pod that exists there is equal to blue state. So if there's already a blue state pod, then do not schedule this other blue state pod on that node. That's essentially what the Anti Affinity is saying. And then we've also got pod disruption budget, which is a feature that was already released in the previous Kubernetes release, but is very useful for quorum-based applications, which says always make sure that there are at least 2 such pods available in the cluster. And so if you're doing a cluster upgrade and there's a system operation doing that, it will make sure that at least 2 pods are always available. Now I'm going to give you an example of taints and tolerations and where that can be useful. Taints and tolerations can be used, for example, to dedicate a node to a particular type of workload. So in this case, we have put a taint on node 1 that says this is a dedicated node, please do not schedule pods here. And we're going to put a toleration for that taint on the green pod that's called green job. And so that toleration says, yeah, I have a toleration for the pod, for the node that says it's dedicated only for green jobs. And so on and so forth. There are many such features and many such actually combinations that you can use. Forgiveness is a special case of taints and tolerations where every node has a taint that says if the node becomes unreachable, if there's some sort of event that happens, then evict pods and evict them after, how long that do you wait before you evict the pods is a toleration that you can put on the pod itself. So here we've got a pod that has a toleration of 300 seconds and another pod that has a toleration of 3,600 seconds. So at t equal to 0, all pods are on node 1. Node 1 has had some sort of event and has gone down. And at t equal to 300, the blue pod, which has the 300 second toleration, will be removed and rescheduled elsewhere in the cluster. And then at 3,600 seconds, the green pods will move over elsewhere in the cluster. This is very useful for ensuring high availability. For example, if a node goes down or a zone goes down, and you've spread your cluster across multiple zones, Kubernetes will automatically move your services to the zones that are available and the nodes that are available. All right, the last feature that I'm going to demo is dynamic storage provisioning. And this is very useful for automating the management and lifecycle of storage. Particularly important for stateful applications where you want to make sure that the storage is always available to your stateful pods. And for this, I'd like to switch over to the demo. I'm going to use the same cluster, 3-node cluster in Google's cloud. That's running 1.6. So the first thing I'm going to show you is actually non-dynamic storage provisioning, which is manual storage provisioning, the way that it used to be done. All right, so in this cluster, I'm first going to list what type of storage is already available. I told you it was a 3-node cluster, and so there's only just the local disk associated with each node. We haven't created any storage yet. I'm going to go ahead and provision a disk in Google Cloud, and I'm going to say I want a 100 gigabyte disk, and it should be of type PD standard, and let's name it manual disk 1. This is an operation that usually someone familiar with storage, probably a storage admin might like to do. But in any case, what we're doing is we're pre-provisioning the storage before our workload is ready to consume it. Let's check that this disk has been created, gcloud compute disks list. And yes, and now in addition to the local disks, you see that the manual disk 1 has been created. All right, so let's look at different ways of using this disk in your application. One way, the not recommended way, frowned upon, is to have an inline pod spec. So in this pod specification, I have actually said, exactly what my disk is, that it's a GCE persistent disk, it's called manual disk 1, this is the type of file system. While this will work, there are many disadvantages to this, as you can imagine. This pod spec is very specific, and it is not portable. You can't take it to a different environment. It can't use a different disk, say, if manual disk 1 we want to change it out. And also, Kubernetes doesn't really yet know about manual disk 1. It's something that's outside the scope of the system. What we really want is a PodSec that's modern and portable, that doesn't refer to the specifics of the storage. At the end of the day, I, as the application admin, do not want to know the specifics of the infrastructure, and Kubernetes is supposed to isolate me from that. So a modern PodSpec would just say, hey, I have a persistent volume claim, and this is the name of the claim. The claim has some of the details, and then the persistent volume spec has some of the details that are specific to the storage environment. So what we've done is we've taken that storage-specific detail and distributed it across 2 other objects. Let me show you those 2 other objects. The first one is a PVC, a persistent volume claim. This is really just a request. It says, I want 5 gigs of storage. That's what my pod needs. Please, wherever you find it, I don't care what type it is, but give me that. And note this thing called a storage class name. In this example, we've set it to the empty string, which is really what's saying I don't care what type it is. But in dynamic storage provisioning, I'll come back to this, your storage admin can set up different classes, a gold, silver, bronze, fast, slow storage class. And in the PVC, I, as the user, can say, yeah, I want the gold class. But for this example, I'm not going to use any class. So the second object is a persistent volume. This is the object that the storage admin or cluster admin would use to give Kubernetes information about the storage that they've provisioned. So here is where the details are, and we've said here, yeah, actually, of the 10 gig disk that you created, I want Kubernetes to have access to 5 gigs of that. And when I'm done with it, I'd like you to delete that disk. And yes, it is a GCE persistent disk with this name. So this is the PV, the persistent volume object. You see how we've done that abstraction and separation of concerns. So let's go ahead and create the persistent volume that's been created, and let's also go ahead and create the persistent volume claim and see what has now happened. So you see that the persistent volume has been created and it has been bound to the claim. And so now, when the pod comes along and it requests the storage, the claim is already there, the volume's already there, the storage is already provisioned, and the pod can now directly write. Kubernetes will mount the volume to the pod, and the pod can die and move to a different node, and Kubernetes will automatically take care of remounting the storage to the new node. And the data will still be there because the PVC remains. The PVC is a constant and holds that claim to the storage. Okay, let's clean this up, and then I want to show you, and so I've just deleted the claim, and since I've set the policy to delete, I'm going to go ahead and show you that, in fact, the disk also has been deleted. So now we're back to the original cluster, and I'm going to show you dynamic storage provisioning and how simple that is. So in this manual provisioning case, there was a storage admin that had to come along and pre-provision the storage, and there was some communication between the user, the app admin, and the storage admin to know, that storage had been provisioned. In dynamic storage provisioning, we want to really kind of make them independent so that the user does not have to even communicate with the storage admin. So first, let me introduce storage classes. I talked about that a little bit. We're going to have the cluster admin or the storage admin create a storage class. In this case, it's called storage class fast, and it's an SSD PD. Note that we're not actually provisioning the storage. The admin is just specifying that I have something called fast. We're going to create this storage class and take a look. Yes, and we've got the fast storage class. There's also a default storage class because this is a 1.6 cluster. Standard PD is the default storage class. And so now we look at the persistent volume claim for dynamic storage, and it's called my PVC fast, and I've requested 10 gigs for my pod, and I've said I want whatever the fast storage class is. Note that so far nothing has been provisioned. There's no pre-provisioned storage, no resources lying around waiting for this application to come up. And so when I create the PVC, let's see what has happened. Not only did I create the PVC, but the PVC has automatically, dynamically created a PV. The storage admin didn't have to do that. And it has also bound the PV to the PVC. And if we take a look, you'll see that the disk has automatically been provisioned as well. So this is dynamic storage provisioning. The benefit is that it's just in time. When you need the storage, that's when it gets provisioned. There's no wastage, and then it creates a separation of concerns. You don't need to call the storage admin or know about the storage admin. And this is as it should be. Kubernetes should take care of the underlying infrastructure for you. So now we're going to clean up. And the PV has been released, and then by deleting the PVC, the disk has also been deleted. We'll go back to the slides, and I'll conclude with a little bit more about our roadmap. So, what you saw in the demo was dynamic storage provisioning. In 1.6, there's a default storage class for each of these cloud environments, and you can see what the default storage is. So we saw that for GCEPD was what we used for Google Cloud. There's also support for user-written and user-run dynamic PV provisioners, which is very nice. That allows us to expand the range of storage supported. The last thing I'm going to touch on is our overall roadmap. And I think with 1.6, you can see our direction, supporting multiple workloads, multiple teams in larger clusters so that you can get the maximum efficiency. And we're going to continue that progress. RBAC is going to move to default. We're also going to add, we've got network policy that's going to move to stable that allows pods to say, this pod should only have access to this part of the network, so that not anybody can reach that pod. Stateful application support, we're going to continue and automate stateful upgrades. We've just added alpha support for GPUs in 1.6, and we're going to continue that. A lot of users are starting to run machine learning and they've been using batch workloads on Kubernetes, so that expands that. Multi-workload scheduling, which is beta, will also graduate and add further features. In terms of extensibility, at the beginning here in our keynote, we saw that there were 2 different runtimes donated as part of the CNCF now. The container runtime interface is a way for Kubernetes to incorporate different runtimes. And we have in this release beta support for the Docker runtime. But in future releases, we will be adding container runtime interfaces for other runtimes as well. And lastly, service catalog. This is a new initiative as of a couple releases ago. It allows Kubernetes to consume and communicate with services outside the cluster. And as part of this, we've been using the Open Service Broker API that a group of companies is working to establish as a standard in this space. This is just some of the roadmap, but it gives you a sense of the overall themes. And again, this is in development and subject to change. With that, I'd like to conclude and say thank you, and welcome to the other talks at KubeCon.